Hello everyone, and welcome to our next lecture. Today we're going to turn into fairness and biases in machine learning. Fairness and bias become crucial topics as machine learning nowadays is used in more and more high-stake applications, such as when we hire people or in deciding whether somebody should get a loan. And even though I think we can agree that there are clear benefits to algorithmic decision makings, where unlike people, machines do not become tired or bored of the same task all over again, and that they can take orders of magnitude more factors into account than people. But at the same time, it's crucial because similar like people, machines can be vulnerable to bias, and this can render their decisions unfair. So we need to really look into that, understand what does it actually mean to be algorithmically fair, and how can we achieve that. Let's first look into real examples that motivate why we need to look into machine learning fairness. The first small example that I would like to give stems from the year 2014, where a team of engineers at Amazon began working on a project where they wanted to automate the hiring processes in their company. So they were given the task to build an algorithm that could review resumes and determine which applicants Amazon should bring on board. But unfortunately, as it turned out, the project was not continued for a long time because it became clear that the tool systematically discriminated against women applying for technical jobs, such as software engineers. How did that discrimination of the tool manifest? Well, from all the incoming candidates, it just constantly downvoted candidates who contained the word woman or women in their application, like I was a captain of the women's team and or they downvoted candidates who went to certain women's colleges. And of course, this then brings in an unfairness in the hiring process that cannot be taken. So why would something like that happen? The problem here seemed to be that the models were trained to vet the applicants by observing patterns and resumes submitted in the company over the 10 years prior period. And as you can imagine, most hires that had been done by Amazon in the past were men. So this basically reflects the dominance in the tech industry of men and led to the fact that the algorithm thought we should just continue doing what worked in the past. Another example for where it becomes really important to consider bias is, for example, the treatment of skin cancer. And nowadays, machine learning models do an extremely good job to specify whether some changes in the skin might be cancer or might be just benign. Here comes the thing though. Most of these cancer detection models are trained on lighter or white skin, and they do fairly well with that task that they're trained for. However, now when they're applied to darker skin, their detection rate becomes very poor. And eventually this is not a very surprising effect because their training data set in general contained just the mainly white and light skin and often no pictures from people with African or Afro-Caribbean or South Asian backgrounds. But what the effect then is that the healthcare for those groups becomes significantly worse and of course brings unfairness into this decision making. Similar discrimination can be observed even outside the public and health sector in proprietary sectors, where, for example, the Face ID in iPhone was shown to underperform on Asian phenotypes. So, for example, it happened that people in Asia had the problem that friends or co-workers could unlock their phone's Face ID, even though the people wouldn't look so much alike also to a human observer. How is that possible again? Well, again, the training data set of the iPhone Face ID just did not contain enough of these faces to have a clear picture on how to tell apart the facial features. And now finally, the same can happen in language models. For example, Turkish. Turkish is a gender-neutral language. So if I want to say he's a doctor, she's a doctor, in both cases I would say o bir doktor Or when I say he's a nurse, she's a nurse, I would in both cases say o bir hemşire. And if I put that into Google Translate now, she's a nurse, he's a nurse, he's a doctor, she's a nurse, both comes out to the same. But here comes the thing. If I translate back from Turkish to English, where in the Turkish we actually should not have any clue about the gender, because the sentence in itself is gender neutral, we get back that he's a doctor and she's a nurse. So there are clear biases that come from the training data, where apparently more texts were about male doctors and female nurses, which then reflect in the gender translation. So you see that there are multiple examples where machine learning can go wrong in their fairness. And how that can happen is basically that the machine learning systems just reproduce biases they have seen from their training data. They are fed data without taking the fairness into account, so the selection of training data is biased. And how can it be that they still do that when after being released? Have they not been tested? Well, apparently they have been tested only on subsets of the distribution, probably again biased ones, that they then think represents the world. But in fact, when presented with the real world distribution, they start failing. Now, how does bias actually enter into a machine learning system? To understand that better, let's look at what are the different parties that are participating in that system, basically. And on the one hand, we have the users. Users generate with and generate or interact with data. And then this data is fed to a machine learning algorithm, and the algorithm eventually presents some results or some decisions back to the users. And in all of these three places, actually, biases can enter. So when we generate data and then feed it to an algorithm, there can be some biases. When the algorithm does some predictions and gives them to the users, some biases can be introduced. And finally, from the user perspective, when the users interact with data or when they generate data, there are biases that can occur. Let's start with this bias, the first type of bias, how the data can basically bias the algorithm, or how the biases in the data can actually fly into the algorithm. And the first of the biases that we can encounter there is a so-called measurement or reporting bias. And that bias usually arises from how we choose the data or how we utilize or measure particular features. You can think of the Amazon hiring example again, where the classifier basically extracted certain features like being a woman or writing the word woman as a negative feature to then downrate the application. A second type of bias that we can encounter is the so-called omitted variable bias, and that occurs if we take important variables out of the decision process of a model. You can imagine a company internally deploys a machine learning model which should predict to them when somebody will cancel their subscription, like for example to a movie platform or something like that. And of course they want to know if somebody is likely to cancel the subscription. Maybe they can send them out better offers or something else, like improve the system just to keep them in the service. However, now imagine that another competitor arises, for example a different movie platform, and they launch their own service with the same quality but maybe half the price. In that case, that's something that the machine learning model, the original one, could not predict correctly. So what would actually happen is that it would give us some wrong estimates because it just didn't take the variable into account that the other service would emerge. Again, then there is a representation bias that can arise from how we sample from a population during the data collection process. So we sample incorrectly, basically. If we think of it in this medical example, like the skin cancer detection, we know that all over the world there are people with different types of skin colors, and we know that they all should be represented in such a medical decision making. Yet, maybe because the data is more easily available, or because it's some curated data set that exists already, or maybe the research is done in some particular part of the world, We just sample people with lighter skin and no people with darker skin, and then we train the model on that. And obviously, we end up with a suboptimal model for all data that was not in the original distribution. And finally, the last type of bias that can come basically from the data into the algorithm is the aggregation bias, sometimes also called ecological fallacy. And that arises when we draw false conclusions about individuals from an entire population. And this type of bias is apparently seen a lot when we deal with clinical trials. So take as an example diabetes. In diabetes, one measures these HbA1c levels, and then decides like whether somebody is like diabetic or not. However, the threshold value when somebody should be classified as diabetic or not differs largely in a very complex way across genders and ethnicities. Hence, if we just take an average over everyone and take that as a threshold, it will not help us as a population, even if we have the perfectly balanced data set. Because imagine that you have now like a group of men and women and different ethnicities, and each of them has their own threshold, and then you aggregate all of them into one threshold where you say, okay, based on this level, somebody most likely has diabetes. What happens then is that the threshold is not optimal for anybody, because for some people it will be too high, for others too low, even though like on average it's correct. The second type of biases that can be introduced into the system are from the algorithm to the user. And the first one is basically inside the algorithm. So we call it also algorithmic bias. And algorithmic bias is something when the bias is not present in the input data and purely added through the procession of the data. So if we, for example, choose a wrong optimization function or a wrong regularization, and then we perform that optimization such that the algorithm itself basically does not benefit every population part alike. It can also happen that the fact how we execute the algorithm just introduces that bias that is closely related actually to this bias of treating the whole population entirely together and then basically ending up with an average threshold rather than an individual one. The next type of bias is concerned with the algorithm's output, and it's called the user interaction bias. And the first of those is a presentation bias. So presentation bias basically is the result of how information is presented. For example, on the web, if a user basically is to click on some content, the user can only click on content that is presented to them, right? So by the decision what the algorithm presents to the user, it naturally determines what the user can click. So everything that's presented to the users is clickable, will get interactions. Everything which is not presented will get no clicks. So, but if it was presented, potentially it would get some clicks. And thereby we introduce a bias because it's just not super clear what elements were presented to the users and what elements were clickable in the first place. Very similar is the so-called ranking bias, and that occurs a lot in search engines because what you can imagine is that the top ranked results, they're presented at the top of the page and they're presented as relevant or important. And of course, nobody really when doing a search wants to scroll down like hundreds of Google pages and will click like the 150th entry. No, of course not. Therefore, people are just more likely to click more often on the elements that are already voted popular, and then basically they become more and more popular. In a similar vein, the popularity bias means that if an item is popular, it tends to be exposed more, and then it basically will get more clicks and will get more and more popular in an upward spiral. However, what popularity means might actually be fake. And for example, you could imagine in some social media platforms, there are trolls just upvoting some content artificially, or on some online purchase sites, some people write fake reviews, and then like the wrong items actually get to the top and then become more popular even though not deserved. And then there are two more biases. The first one is the emergent bias, which occurs basically when real users interact with the platform, and basically when the population that the platform was for has different values, or the values of the population evolve. So we start designing a platform with some certain values in mind, but then culture change, population change, society change, And then basically the values are mismatching between the original setup and the final site. And the final bias here that we have in terms of the algorithm is the evaluation bias. And that basically happened in all the examples that I presented. They were all released in a good belief that the systems work well, like Shelby for hiring, for skin detection, skin cancer detection, for some face ID. But the problem here was that the evaluation apparently was as biased as the training, so we just took an inappropriate or disproportionate benchmark to evaluate the algorithms. Finally, when we look into how does bias emerge between users and the data that they generate, or the data that has basically been generated by other users and now is of importance for new users, and the first bias that we see there is the so-called historical bias. So that means that existing bias from our societies are just going to be directly translated into the technical systems, because we just sample and reproduce what has been done before. I think that is basically what happened, for example, in this Amazon hiring example. They hired more men in the past. They basically, like, internally, like on a human level, decided that some, like, the men that they hired were a better fit. So the algorithm just barely reproduces what it has seen in the past. A second basically is a population bias, where, like, we have some statistic and demographics of some user population that the platform or the service was potentially targeted with, but then now suddenly a different population starts using the service. And one could argue that this might be one of the underlying problems with the iPhone in Asia. So the iPhone was originally launched for the US market, and it was basically trained on the phenotype of people who were of the majority of, like, who lives in the US. And then when being launched in a different market, it just doesn't fit anymore. Of course, they should have taken care of that, but it might be an explanation. And another bias that we in research also have to be very much aware of is the so-called self-selection bias. So if we want to run a study where we want to find out about individuals and about their beliefs, their values, is that we always have the self-selection bias. Because if you ask somebody and they basically take the time to reply to your poll, this already is a very particular population. Or take also Google reviews, like, who writes reviews usually? It's not the people who are, like, averagely happy with what they went for, but it's somebody who either had a really bad time or had an amazing time. So you basically have these extremes. And this is through this so-called self-selection bias. And finally, we have a social bias, and I think that's not only limited to machine learning, but in general, and translates then into the technical systems spec. And an example of this is that we have to rate something, for example, and we give it a low score, but then we see that other people, potentially people who are more experienced than us, they give it a higher score, and then suddenly we start thinking, have I been too harsh with my judgment? Should I maybe change my score? And then basically you change the score. That's also something that happens a lot in research when very junior people review papers and then are presented with papers from other people who are potentially more senior, and there's a big discrepancy how they rated the paper. Then somebody might just start wondering and questioning, like, have I given the right score here, or should I maybe adjust more to basically what the others think? So now that we are aware of what different types of biases we can have in data or in machine learning system, at what parts they can be introduced, the question is, how can we actually quantify them? And this brings us to the quite interesting area of different ways how to measure fairness. And all the definitions that we basically have currently, they measure some things. They measure fairness, for example, from the perspective of one individual. Others measure fairness from the perspective of a group. And we have basically multiple examples that we're going to walk through now. All of these definitions are basically out there. There is no right or no wrong definitions. And it's sometimes like even impossible to satisfy multiple of them at once. And then it's always the question of the application designer to decide which of the definitions should be the most suitable one for the given application. Let's start off introducing the running example that we're going to use when talking about the fairness metrics from now on. So the example that we're going to talk about is that we take a very simple machine learning model that could be deployed, for example, by a bank. The model just takes one input feature, namely the income of a person, and then outputs whether the person should get a loan or not. And this decision whether somebody should get a loan is based on historic data. Here in the plot, I'm now going to denote by the fully colored circle that somebody paid back their loan, and by these gray circles that somebody did not pay back the loan. And of course, the bank wants to have kind of an optimal outcome, that they only give loans to people who are similar to those who paid it back in the past, and not to those who are likely to basically not pay it back and fail. So what should the bank do based on the historic data that we have? They kind of want to find a threshold, like for income, where basically if we draw a line and the people above this threshold, they should get the loan, and the people who are below this line should not get the loan. And I just put one possible line in here where we can see that basically above the line, most people actually paid back their loan. There's one false positive. But otherwise, on the lower side, where people don't get a loan, also most people didn't pay it back. There's one false negative, so this person would have actually paid back the loan, but we would have to lower the threshold so much to introduce them that those would also be included who didn't pay back the loan. So it might be for the bank the optimal solution at the moment. Becomes now a bit more complicated if we consider more than one group. So imagine you have at a bank as before, but of course their groups of customers is not homogeneous. They have customers from different regions, working in different professions and different stages of their lives. Or for simplicity, they also have customers that separate in a binary attribute, and we could say half of them are men, half of them are women. And now what demographic parity would expect us to do as some form of fairness is to give each subgroup the chance of a positive outcome at an equal rate. So all of them should have a positive decision at an equal fraction. Take, for example, the data from before, and now this time we have two groups. So here we have the first group, for example, women, and then the second group here, for example, men. And so now if we take a threshold somewhere in the women's group, then we see that 4 out of 8 women should actually get a loan. So then in the second group, we need to have the same rate, basically 50% we have here. And then if we want to have as many men having a loan as women, then we need to set a threshold here. So basically then half the men should also get a loan. And what you can see is already that the income threshold needs to be lower, because otherwise if we set it at the same rate as we set it for the women, then basically only 3 out of 8 men would get a loan and the rate would not be alike. If we formalize this intuition, what we end up with is the following definition, namely that the probability of having a positive outcome should be the same whether or not the sensitive attribute is 0 or 1. So whether they are women or whether they are men. And what can go wrong if we have demographic parity here? Well, as you can already see, for a bank, this definition would definitely not be ideal, because in the second group, here you see that 3 out of the 4 people who actually got the loan will not be able to pay it back probably. So demographic parity kind of assumes that people in the second group have now the chance to behave the same way as people from the first group, but that might not happen. So for example, these women here, they are in solid jobs and they're in a stable social circle, but for example, these men, they decide at some point that they want to travel the world, want to quit the job, do whatever. And then basically there's no social network to back them up, and they will just fail in paying their loan. So they need to be given enough chances, enough support to still be able to pay that back. So if we do not change the social structures, then basically this will reinforce the stereotype here that the men are actually not really able to pay back their loans. And then basically that will be reflecting badly for them and in future decision makings. So when is actually a good time to use demographic parity? And actually demographic parity should be used if we want to change the status quo. So if, for example, we want that more men here get a loan. And we should also use it if we are aware of the historical biases. So we might be aware of the fact that actually we did not have so many men maybe paying back their loan in the past, So potentially we can give them a better chance to improve basically the data in the future. Or we can also use it if we have a plan how to support the underrepresented groups. And for example, university admissions often aim for some form of demographic parities, where they give more admissions to students who come from a more difficult background. And in that case, these students have a high academic potential. But for example, due to the situations, their education might have been disrupted, or they have been in some personal disadvantages. And then these students, they would achieve very well, and they can if they're just given some extra support, for example, before beginning the degree, or if they get some additional mentorship or scholarships, and then like the positive outcome will indeed be alike for both these groups. The next metric, basically the equal opportunity metric, goes a bit further and tells us that each group should get a positive outcome at an equal rate, assuming that people in the group qualify for that. So because if you remember, like last time we saw that actually many people in the second group did not really qualify well for the loan and still would get it, and this is supposed to be fixed through this equal opportunity. So imagine we have the same data as before, and what we then want basically is that the true positive rates, so whether they should have been given the loan and like whether they actually deserve the loan, should be the same. So imagine we take the threshold here, and then basically 4 people still get a loan in the first group, out of which 2 deserved it. So 50% of the people actually did deserve the loan, like whereas like the other 2 who did deserve the loan, they are basically under the threshold, so they didn't get the loan. And then basically for the second group, we need to set it such that like the same true positive rate holds. So we have again 2 positives here. And then we should set the threshold such that only 1 positive basically gets that loan. And if we were to turn it into a formal definition, it looks pretty similar like the one before, but we have another factor here. So the probability of having a positive outcome should be equal for both groups in case they really do qualify for a positive outcome. So like if their true label is really 1. And what could go wrong here? Well, if we want to give out many loans in the group 1, that means that they'll have a higher acceptance rate. And then in turns, we also need to give out many loans in group 2, and this might give us some false positives. So then we'll have people who are suffering basically from the wrong decision. So everybody here basically in that group will fail paying back their loan, and then this will negatively impact their credit score also in the future, and they will not get loans in the future again. So they will be also more harmed than basically people in the other group. But when is it a good idea to use equal opportunity? This is the case if we really want to predict a positive outcome often. So if it's like good time to give out money for a bank, and like interest rates are low and the bank just really wants to get rid of their money somehow, then they should want to give out many loans, and therefore this metric would be kind of good. And also, it's good if false positives are not costly. So basically, these points, the gray points above the threshold, are all false positives. And for a loan case, they are actually costly, like for both parties, as I explained. Like the bank will lose their money in the worst case, and the customer will suffer from having a worse credit score. So equal opportunity is actually not a good metric here. A good metric for equal opportunity might be something like fraud detection, for example, for credit cards, where we want to notify the users for everything that like goes possibly wrong. So we do not want to miss an occasion of notifying them when their credit card might be misused. But it's also not too bad when we call them too often and just make them verify some transaction, because it costs nobody anything, but it just makes the service much safer. So if you now want to go even a step further and restrict the previous definition a bit more, then we could go for the equalized odds definition. And equalized odds extends the previous definition by the false positive rate, so requiring the 2 groups to have the same false positive rates as well. So imagine that's our setup as before, and we take the threshold for the first group here. then our true positive rate is a half, so 2 out of 4. So 2 out of these green points who would actually deserve the loan did get it, basically. And then the false positive rate is 1 out of 4. So basically 1 out of these 4 gray ones that did not deserve the loan actually still got it. And then we would have to set a threshold for the second group like this, such that basically the true positive rate is half still. So basically 1 out of these 2 points who do deserve the loan get it, and 1 out of 4 illegitimately got it. So putting that into a definition, it's roughly the same as the previous one, just taking into account basically both types of outcomes, the positive and the negative outcome. And one thing to note also is that this definition here is relatively restricted, so it might sometimes fail to produce high accuracy results. When would the equalized odds be well suited? Well, that would be, for example, if we care about getting many positives, but we also want to minimize the false negative rank. So in fact, that might actually be the metric that is the best suited for our bank if they want to decide who gets a loan, since the bank has no interest in getting high false positive rates because they might lose their money, but they do want to also get a high true positive rate because they want to give out loans and make money with that. Now, in all these definitions, also when I always told you we want these these thresholds to match completely, so the true positive rate to be the same one between the two groups, what we actually mean in practice usually is that they should be roughly the same, so they should be similar. Sometimes imagine like now for the group 2 there would be one of those points missing, so in that case it would be impossible to get to exactly the same false positive and true positive rates. Then we would just try to go as closely as possible to the correct rates. Let's finally, now as a last definition for group fairness that I want to introduce today, we have overall accuracy and treatment equality. Why do I put these two together? Well, because I think they kind of refer to the same side, like to the two sides of the same coin. Basically, what we want is an overall accuracy, that each subgroup should have the same prediction accuracy. And what we want in the treatment accuracy is like that the errors of the classifier match between the different groups. So I think that's pretty much the same. And what we have here, basically, if we want the same accuracy for everyone, like in this setup, for example, if for this group 1, we set the threshold like this, then we have these 2 green points correctly classified and then these 3 gray points correctly classified. So that means that 5 out of 8 data points are correctly classified. If we want the same story basically for the other group, we could just set the threshold here. Basically then like this purple point here is correctly classified and then these 4 gray ones. So overall basically we don't get the same opportunity, so like more people from the second round, from the second group are actually rejected the loan. But in applications where we value the true positives and the true negatives equally, then this might be a good way. And so if we were to define that, basically is that the accuracy of either group should be roughly the same, or like for the treatment equality, so the false negative rate divided by the false positive rate for both the groups should be also roughly the same. And here in our example, if we look at the treatment equality for the group 1, what's the false negative rate? Well, 2 out of these 4 here are like false negatives, and the false positive is 1, so 2 divided by 1. And then in the other example, also 2 out of these incorrectly don't get the loan, but this one like incorrectly gets the loan, so it's also 2 over 1, so the treatment equality is also fulfilled. Now that we talked about the group fairness definitions, we should also mention that other fairness metrics look in the individual fairness, so not like belonging to a group, like for example men or women, but just every individual on their own should get like a fair classification. And therefore, like one metric that was introduced was the fairness through unawareness. So a classifier would basically satisfy this definition if no sensitive attributes are explicitly used in the decision making. So imagine you now give the loan by the gender, basically. So you don't give the gender into the model as a feature, and then just let the model classify. So what that means, like if we define that we have an applicant I and J, and the features, apart from maybe the gender features, are exactly the same. Then what we want is that the predicted outcome is the same for applicant I and for applicant J. Going a bit further, and like more elaborate and generic than the previous one, is the so-called fairness through awareness. And we again capture fairness by this principle that similar individuals should have some similar classification. And the similarity of individuals can be described here for a distance metric. So basically for the fairness metric to hold, like for like two individuals getting roughly the same output, like they should be roughly the same according to this metric. So the definition here is a bit more complex, but we can think about it like as V being a set of individuals. So for example, everybody who applies for a loan. And then we have this distance metric between applicants, and like a mapping function that maps basically from an applicant or like from a set of applicants to a probability distribution over the outcomes, so whether they get or get no loan. And D is a distance metric. Then basically the fairness is achieved if we have like a distance and outcome of these like predictions for both the applicants, if they are basically relatively similar. So if their distance is like measured by K, then K is the upper bound on how much different their outcome for them can be. And like what possible distance metrics for K could be, for example, we can say that like the distance is 0 if all the attributes apart from the gender ones are identical and they're set at 1 otherwise. Or another example is like, for example, if the candidates still differ in their age, for example, we could take the age difference in a somehow normalized way. For example, like two candidates and then like they differ in age but all the other features are the same. Then we just take the normalized age difference, for example, normalized by dividing through the maximum age difference in the data sets or so. And now that we basically know how we can achieve fairness, let's look into how we can really implement that. So we have all these measures, what fairness could be, and now how do we get this actually into the machine learning systems? And there are 3 parts basically where we can introduce it: in pre-processing, in processing, or in post-processing. And I'm just going to introduce those a bit more in details. What we do in pre-processing is basically that we want to transform the data such that already in the data the discrimination is removed. So if our algorithm allows us to modify the training data, then pre-processing is applicable. And this recognizes that the problem often is in machine learning the data itself. For example, in the Amazon example, we only had data from mainly men being hired. So that might actually be unwanted. And like, so there's already bias in the data. And then we could just alter the sample distribution and protect basically the sensitive variables and like make them more equal. So we train then the model afterwards on a so-called repaired data set. And we can think of it that pre-processing is one of the most flexible parts of the machine learning pipeline, because we have already like many pre-processing things. So usually data is cleaned before it's fed into a machine learning algorithm and altered, normalized, transformed. And here we do not make any big assumption on the algorithm that is later used to treat that data. So it gives us a lot of flexibility. When it comes to in-processing, we have to go a bit deeper into the machine learning itself, and we have to change the learning algorithm in order to remove the discrimination. And if we have full access to the machine learning model, then in-processing is really useful, because we could either, for example, introduce a change in the objective function, or we could impose a constraint that basically then lets us treat the data differently and balance out some unfairnesses while processing. Sometimes the problem here is that basically multiple objectives might not be perfectly achievable at the same time, and we're going to talk about it more in detail towards the end of the lecture. But if we usually optimize a model for having a good accuracy, and now we introduce additional constraints or optimization functions to also have good fairness, this basically might then like get accuracy to suffer a bit. A problem here is also that often having these additional processors or additional constraints requires them to take different machine learning libraries or to extend the existing ones, which arguably is more effort than just like taking data and plugging that into the algorithms that we do already have. As a last option, what we could also do is post-processing. So in post-processing, basically we leave the data as it is, and then we feed it to a standard machine learning algorithm. But then we alter the model output. So we would do this post-processing on a holdout set, which was not involved during training. And like we treat the algorithm as a black box. Then it helps us, for example, to discover, okay, we now predict in this holdout set like this amount of women, this amount of men, and then so many women got a loan, so many men got a loan. If less men than women got a loan and we don't fulfill the quota that we basically wanted, or we don't fulfill the fairness metric that we wanted, then it might actually be possible to just suppress certain model outputs for one group and then like scale up the other one for the other. Or even like we see that like men do not get enough loans, then we could just manually change the value for men, for example. So it's often quite difficult to understand which type of approach will benefit a given scenario the most. And they all have their different advantages and disadvantages. And basically it depends on the application which one is the most suitable one to apply usually. To look a bit more deeply into what are the possibilities that we do have in the like concrete steps, how to concretely implement those. And if we want to have this pre-processing fairness, one thing that we can do is, for example, so-called blinding. So we make the classifier immune to one or more sensitive variables. So imagine there's our group of individuals and you see there are more women, for example, who got a loan than men. And then what the blinding would do is to make the model immune to the sensitive attribute and make it treat all these groups alike. Some work basically also takes omission of sensitive values as a form of blinding. Omission just means basically we do not present the model at all, for example, with any gender-related features. But in my opinion, it makes sense to distinguish between this immunity and omission, because omission just refers to not including the sensitive variables. However, the problem is that there are always some correlated variables. So for example, if we have gender, like then the correlated attribute might be, I don't know, size, or so that's also processed. Or if we do not want to look into somebody's income group because we think it's too sensitive, then we might still be able to see their postal code, and the postal code usually also gives an idea on is it a rich neighborhood or a poor neighborhood. So we might still get all of that into the classifier, even if we explicitly take some variables out here. So basically then we don't have a true blinding, but we only have some form of like less sensitivity. But if we do omission, it might as well result in the model eventually being more unfair, because we do not detect the correct proxy variables, and because the model might then just overemphasize on those and just not give a very good value anymore. Another way what we can do is to do sampling and subgroup analysis, and I think sampling is kind of the most easy data science solution. Imagine now we have basically these two groups here and like different rates. What we can just do is basically we upsample the group that we have too little, so we basically include just the same male individual here twice, and we downsample the other group, that basically eventually we have the same number of features. Here, of course, it makes a very big difference how we select these individuals, and unfortunately, if we do that without care, sampling could propagate biases even more. Like if, for example, then the group of the underprivileged individuals, so the smaller group, if we upsample the same one multiple times, it just doesn't necessarily add more information. So eventually we might just end with a like even worse result for this group, and like also negatively impact the performance. Also for outliers it can be very problematic because there's nothing to upsample them with. So like we would extend them basically and upsample them, and then they just might ruin the prediction performance. As a next part, I would like to talk about methods on how to get the in-processing fairness done. And the first way how in-processing can be done is very similar to the pre-processing, like to the sampling basically. It's called reweighting. So like reweighting can also be done as a form of pre-processing, but it can also be done during the training. And what we do is we just change the impact of certain instances on the prediction of the model to have a fairer handling of the sensitive variables. So we just basically would alter the weights to get more information from certain individuals, and upscaling the weights of some individual on the optimization that we perform can have multiple purposes. For example, we could simulate some form of frequency count with that. So instead of just like upsampling the one individual twice into the data set, what we could also do is like we just weight their impact double. And for example, for these existing individuals here, for the women, we just weight their impact half. And so eventually like both groups would be equally weighted without having to basically take out some individuals entirely or replicate some others. What we could also do is to basically have a higher or lower importance on some sensitive training samples. So for example, if we know we have very little samples with a particular set of attributes, then we could also just weight those up such that we then have basically more insights on them. The only problem with reweighting is that it might also not always end up in the best performance, and it makes it even less explainable how a model reached a certain decision basically, because all the samples now have like even disparate impact on the model predictions. And we are going to cover explainability in the next lecture. Then you'll see like where this importance comes actually from. Another way how we can do in-processing fairness is through just changing the learning itself, and that can be done, as I already said, through some regularization or constraint optimization. And that usually incorporates extending a classifier's loss function such that we penalize some form of unfair outcomes. So classically, regularization penalizes the complexity of machine learning models. So like for example, L2 regularization forces the model parameters to still stay kind of small. And in a similar way, we can also introduce that for fairness. And in the constraint optimization, we can just, for example, approach that to include notions of fairness in the classifier's loss function, which then looks in the confusion matrix during training, and then basically like upweights some loss based on how well we do on that. Unfortunately, these changes in the loss function sometimes lead to kind of unstable training, where then like subtle changes in the training data can affect the performance significantly, and then yields a very high standard deviation, which is not always desirable. Finally, what we can do to have some post-processing fairness is like calibration or thresholding. And in calibration, we just look at the probability outputs of a model and then try to make the possible outcome, the positive outcomes match between the groups. So we would ensure that the positive prediction number is equal, for example, between the groups if we want, for example, demographic parity. So imagine like you observe the model then on the fly, like doing some predictions, and you see, by now we have given so and so many women a loan, but only so and so many men. Then you can, for example, just alter the decision and just calibrate the model to basically give more loans out to men. And thresholding operates in a very similar way. If you now think about the model not giving out like a final decision, like yes or no to a loan, but a confidence, like for example, where one expresses I'm very confident to give the person a loan, and 0 outputs means we are like very little confident to give that person a loan. And then what we could see is, for example, if we give women a loan once we are confident for 80% that they would pay it back, we could, for example, give men a loan when we have a 70% confidence already. And thereby we would have just much less like inequality between the two groups. It's basically similar like the thresholds that I showed you in these diagrams, where for one groups we have this income threshold higher than for others, just on the level of model outcomes. Now that we have seen basically how, like, what fairness means, how we can get fairness, I wanted to make a small connection to a prior lecture, namely the one on differential privacy, and just show you a bit how, like, sometimes different trustworthiness objectives can also stand in contrast with one another. And like the first thing I wanted to mention here is that we saw already empirically that differential privacy can reduce accuracy. And like multiple people, like there are multiple reasons why that is. Like the first one is, of course, we add some noise, and then if we add noise to something, we lower our signal, and if we have a lower signal to noise ratio, then basically we cannot learn so effectively anymore. And one particular aspect is also though the clipping. So like imagine like we have here our original gradients. Most gradients go in one direction, one gradient goes here. If we then now take an average gradient, or we aggregate all these gradients, like the gradient like direction that comes out is this one here, and it's like roughly still the same as the original ones, and like only very little influenced by the outlier. However, now if we have to clip these gradients, then basically those gradients lose their impact. This gradient here gets more impact, and our gradient direction is more perturbed. So over like training, we might get like less and less to the optimal direction. And you can imagine that this is even more a problem towards the end of training, because when we're at the end of training, what happens is that basically all the inlier data points, they're already well learned by the model, so their gradient is already close to zero. But for the outlier data points that the model is not good yet on, then basically they still have large gradients. And you see here basically the gradient direction will be more perturbed, and the model will be updated more to the wrong direction. Now here comes the thing. This is a problem. However, it is a disparate problem. So in differential privacy, the accuracy reduction actually depends on the subgroup. And it was found out that differential privacy harms some subgroups more than others. In particular, it harms small subgroups more. And intuitively, that makes sense. So if we think about like, if you have already less signal and then you add the same amount of noise, then you already get less out. But we can also look at it empirically. And basically, I just wanted to present some work that has been done on the intersection of DP, SGD, and like fairness. But it's like similar results would be, for example, also observed with the Pathé algorithm, because also Pathé is not really able to learn from basically unbalanced data, because if you have like one data point from a like subgroup in every teacher, then no teacher will learn anything about them. Or if you have like the data of the small subgroup in one teacher, then this teacher is like finally able to learn them, but their vote in the final histogram will have so little impact that again, like the final outcome might not contain enough information on them. So let's look into what concretely the results show when we train with differential privacy. And here in the first figure, what we can see is like the accuracy of some like skin cancer detection on like darker and lighter skin. And what we see is that if we have non-differential privacy, there is a gap. So the model is much better on the lighter skin than on the darker skin. But that gap is not extremely significant. It's still large, but not huge. But now if we look into the same model trained with epsilon, so here an epsilon of 9.16, you can see that both groups suffered in utility, but the gap has become significantly larger. And if we tune epsilon down, so if we implement more privacy, you can say that this gap is becoming more and more severe. So the difference on the subgroups gets bigger and bigger. So we can say that the like underprivileged subgroup is harmed much more. And if we now look at how does the subgroup size really influence the accuracy, so this diagram here can be read as follows. Like, we assume we train with a non-private model, and then we train the same like model with privacy again, and we look how big is the accuracy difference. So here, this is the accuracy difference. Like, does it get worse or does it get better? And what we can see is that basically, especially for smaller subgroups, so below 1,000 individuals, with DP, accuracy gets much worse. And like, the bigger the subgroups become, then with differential privacy, the harm is not so bad. It can be roughly equal, even sometimes DP can be a bit better. But the smaller the subgroup, the less represented somebody in the training data, the more they are harmed by privacy. And if you think of that from an ethical perspective, it's a big problem, because usually people who need the highest privacy, because they are just the most outliers, they are already underprivileged. And if by giving privacy we harm them even more in fairness, that's of course undesirable. And what we can also see here in the last diagram is basically the disparate effect holds over all model accuracy. So like, we could say, okay, if the model is already pretty bad on the lighter skin, like, will that help? Basically, like, will we then get just at least equally bad alternatives for the darker skin? And the answer is no. The answer is basically overall model accuracies. By using DP, we will still harm the subgroups more than if we don't do that. So you can see here that there is a discrepancy. Also, like we said already, some fairness definitions might be so strict that they give us non-ideal combinations with accuracy. So for example, the equalized odds might not allow us to train a good model. So there are trade-offs. Like, if we train privately, then we cannot get like good fairness. If we train like fair, we might not get good accuracy. So we always somehow need to balance that out. And that brings us to the current challenges that I just wanted to mention in fair machine learning. And the first one that we do face is about the definitions of fairness, about like how to synthesize them basically. And as we saw in today's lecture, there are just many partially opposing definitions of fairness, and there is no correct one, but the correct one basically should be chosen by an engineer usually, or like the person in charge of deploying the machine learning or the application, just to fit that application. But usually it's nearly impossible to understand how one fairness solution would basically perform under another fairness metric. And it also seems not reasonable usually to let an engineer decide basically on like what we want as a society. So the question should be like, how can we get to like one simpler notion of fairness, and how can we also then really enforce it? Given the definition of fairness then, the next challenge that we currently face is we want to find out more easily if something is unfair. So it would be great if we could just look at a data set or look at an algorithm and beforehand just say how fair or unfair is that, such that we can take the necessary adjustments in the training. The next one relates to like what we talked about just before, the trade-offs. Fairness decreases accuracy. If we want privacy, we degrade fairness, and all of that kind of hangs together and gives us somehow non-desirable trade-offs where all these aspects that we want cannot be achieved at the same time. And finally, and I think this is a challenge that goes beyond pure like machine learning fairness, but it's the desire to go from equality to equity. And so many literature definitions that we have on fairness, they nowadays focus on equality. So each individual or group should be given the same amount of resources and then basically get their outcomes. However, it might just be that some groups would need more resources to achieve the same outcome, for example, because they're underprivileged and they have more difficult backgrounds. So in that case, we should focus on the equity and give them more resources to achieve what they really need to succeed. And basically that's a challenge that we face in society, but that would be great to integrate also in our machine learning systems that take valuable decisions on our lives. And with that, I'd like to thank you for your attention today, and I'm happy to see you all in the Q&A session next Wednesday.